Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Alright, lecture 101, electric potential energy. Let me first remind you about work. Who remembers how to calculate work? Anybody? Force
times
displacement, right?
yes.
So let's imagine I have a hill, right? I've got a bunch of little delta x's. So this is work 1, work 2, work 3, work 4, work 5, and all the way up somewhere near the top of the hill, right? So if I want to calculate the work to, say, push a big, heavy boulder, I should give myself arms to push, up this hill, right? And let's assume I'm rolling it up the hill and that the rolling friction is very minimal, so there's very little energy lost to that rolling friction. I push this brick up the hill, I can calculate the work by simply adding up all these little works, right? Work me would be equal to work 1 plus work 2 plus work 3 plus ... right? Until I get to the top, yes? But of course that's, it's kind of tricky to calculate because you'd have to know how many calories you were burning per minute and use that to somehow figure out how much work you actually did, right? So perhaps a better way to look at it, right, is to, let me just write that we could, if we wanted to, we said this was A, and this up here was B, where I'm going with it, right? So I start at A, I go to B. Right, we could write that as some kind of integral where these little W1, W2, these are very small little intervals. So it's the force I'm applying times a very small delta x, right? We have a lot of them. That could be this force dotted with this distance that I've moved, right? And that would be the work that I do if I go from A to B. Sounds like a bomb, doesn't it?
Yeah.
Right? And I'll call that work me. Again? That's kind of hard to calculate though, right? Because knowing what force I'm applying and stuff is tricky. So I could think about, I don't have another colored pen, what if the ball was at the top of the hill and I just let it go, right? We know that the hill has got some height, h, right? We know that the potential energy and gravity is, okay, that's really annoying. Let's pause it here and we'll pick it back up when we have power. Okay, fortunately we have some backup power. So, where was I? Yeah, so let's let it roll down the hill instead, right? And we can calculate that work easily enough. This is, we'll call it W gravity, right? And that's going to be equal to going from B down to A times, we'll call it F of gravity dot dl. I'm not going to worry about the details in there, but we see this is something we can actually compute, right? And so we can write, though despite this force will be the negative of this force because it acts in the opposite direction. Because I've gone from B to A, right, we can see that the work for me is just equal to the work for gravity going in the opposite direction. So now I want to look at this in an electrostatic context. So let's just bring in a test charge, okay? Call it, or not a test charge, we're going to bring in a charge. Oh, we're only going to bring in positive charges, okay? Things change a little bit if you bring in negative charges, but let's not worry about that right now. So I'm going to bring in a positive charge. How much work is it going to take for me to put this charge, Q1, right here? Bring it out from infinity, bring it in, and plunk it down right there. How much work is involved? Anyone want to have a guess? Ignoring gravity, so there are no gravitational fields around. If there was, the mass of these things is negligible. There are also no charges around yet, right? So there's nothing to oppose me bringing this in, right? So the work is 0, right? The work is 0. So we'll call it work 1 equals 0. Now I bring in a second charge, right? Just kind of bring it in along some path, plunk it down right here. That's charge Q2. How much work is involved in that? And this, of course, is this is the work of me, right? This is me doing work, bringing it in. Well, let's use our hill analogy, right? And use that same way of thinking to figure out what this work is. So let's not worry about this yet, because we know it's going to be equal to letting it roll down the hill. So we're going to let it roll down the hill, okay? So we know that these guys are separated by some distance, call it r, and we're going to let this go backwards. So let's calculate what is the work, and we'll just do E for electrical, right? This is the electrical force doing the work now, pushing it back out to infinity. So this will be an integral from r to 1, that's the distance between charge 2 and charge 1, right? Out to infinity. And I'll talk more about the path that it takes in just a minute, but for now, let's just let it take a straight path straight out, okay? And we know how to do this, right? This is going to be K, Q1, Q2, this is just the Coulomb's law, right? Over R1, 2 squared, dotted with dl will give us just the dr, right? So now we just need to look at an increasing separation, okay? Don't worry about how we went from dot dl to this just yet. We'll talk about it in a minute. But this is the integral that we have to do. This is the thing we're going to sum up. This is the Coulomb's law, right, for moving a charge for a small distance, right? So here's the force. It's just equal to whatever the Coulomb force is for things separated at this distance r, right? And then we're going to move it a little bit, right? So force times the distance that we move it, yes? If you go back to lecture 73, I do the same thing for gravity, and I do it without calculus, okay? But honestly, I think it's easier in this case just to use the calculus that we know, a little bit, right? Just the formulas that we have at our disposal, right? And the formula that we want to use is that the integral of x to the n is equal to 1 over n plus 1 times x to the n plus 1 plus some constant c. The constant c is not going to matter because this is a definite integral, so we'll take a difference at 2 points, right? And so that constant is just going to get subtracted out. So let's pull out the stuff that aren't really involved in the integral, right? We can pull out the k, because that's a constant. The q1 and the q2, also constants. And then we'll have the integral from r21 to infinity. I'm going to write this as r, I'm just going to write it as r for now, to the minus 2 power. That's the same thing as 1 over r squared. And then dr, okay? And so you can kind of see what needs to happen. We've got r to the minus 2, so that means that n is minus 2. And minus 2 plus 1 is minus 1. So that's going to give me a minus sign, k, q1, q2, and then the exponent in r is now going to be the minus 1 power, right? Because minus 2 plus 1 is minus 1. So this is r to the minus 1. It's the same thing as 1 over r. But evaluate it from r12 out to infinity, okay? From here out to infinity. And so what does that end up being? That ends up being, well, we're going to have 1 over infinity, of course, is 0, right? So we're going to get 0 minus, now we do it from at r12, so that'll become minus, a negative makes it positive, k, q1, q2, over, substitute in r12 for r, okay? And so there is the work that we get, and since the electrical work is equal to, from going from infinity to this point here, is the same as the work I have to do in going from infinity to this point here is the same as the work that the electric force does going from here out to infinity. So this can also be the work of me, you see? And that's for this first charge Q2. Okay, so does that make sense so far? Right? Just plugged it in, right? Did the same kind of integral we talked about last time, which is just a grand sum, right? Use the quick shorthand formula for it, how to do it, right? And we get an answer. And this is the same answer that we got in lecture 73 for the gravitational potential energy, okay? This 1 over r dependence. So the force has a 1 over r squared dependence, and the energy, or the work, has a 1 over r dependence, all right? All right. Now let's talk about what about the work equals F dot dl business? What's wrong with this crazy path here, right? Why are we doing this straight, going from one separation distance out to another separation? How did I turn it into a 1D problem, right? This is a 3D problem, right? How did I turn it into a 1D problem? Well, the short answer is that you might remember that this electric force is it's a central force, right? And central force is as distinct from other types of forces, like say friction is not a central force, right? It doesn't depend on the separation distance between two things, right? It just depends upon the velocity, really, right? So if I were to take a path, right? There, let's do it this way. How much work did I do, right? If I start out here, so I've done no work yet. I push this charge in. Now I've done some positive amount of work, right? Maybe, let's just call it, a joule it took. Okay, a joule of energy it took to move this from there to here. And then I let it go, and it goes back to where it started from. But I didn't have to push it because the electric field just pushed it for me, right? So that's like negative work. Okay, so if I had some kind of mysterious car that could, burns gas going forward, but when it's driving in reverse, it makes gas, right? I basically get all my energy back, you see? Yeah. So the work done going from start to finish back to start again is zero, right? Yeah. So this is kind of characteristic of a central force, that you can write it as just a function of some separation distance, okay? And we also call them the conservative forces. And the characteristic of a conservative force is that if you start at some point A and you travel any path and then you come back to A, the work done total is zero, right? Yeah. Just like what we just did here, right? I push it. That takes work on my part, but then the return trip is paid for by someone else, you see? Yeah. So the kind of the net is zero. So we can replace, let me just write it this way. So this is on the issue of this. I can replace an integral of some crazy path, even if I curl around, right, into an integral of just this. Does that make sense? Yeah. The crazy path doesn't make much difference. It's only if I change the separation between these. So imagine, I don't think we need this anymore. Don't need that. Don't need this. You might also remember that we can define the potential energy as the negative of the work, right? So we could write that the potential energy U is equal to minus, this is for the electric charge, for a point charge anyways, is minus K Q1 Q2 over R12, the distance between them, okay? Okay. That's the potential energy for that. The work going from A to A, right, can be broken up into the integral of the work going from A to B, dW. So I can just, if I write this, AB dW, and now I'm going to change the sign, right, minus, that's the same thing as flipping this around, right, then this is equal to zero. This is what you get for a conservative force, okay? Which means that if I have a charge, let's say here, and I've got two locations, let's say Q2 is here, but maybe I could move it over here as well, okay? So it's going to move over here somehow, over some path, all right? And the distance between these 2 points is the same separation distance. If that's the same separation distance, right, then they take no work to go from here to here, you see? Yeah. As long as I don't change my separation distance, I can move, and it won't take any work, all right? And so we can draw, let me just draw on this. Remember what the field lines would look like, right? Here are my field lines for this charge. I'm assuming it's positive. If I were to draw a circle of constant radius about the center here, any path along here, right, is always the same distance from the center, which is where my charge is located, right? Yeah? Yeah. So following this path would require no work at all. Okay? And we call such paths, really it's a surface, right? Because this is 3 dimensions. So this comes out of the page, curves around. It's like a globe around the center of this, right? So imagine a globe with a charge at the center. That spherical surface, is an equipotential surface, okay? All right. That means it takes no work to move around that surface because you're not increasing or decreasing the separation between you and the charge at the center. You see? Yeah. Yeah? So that's an equipotential surface for a point charge. That's pretty straightforward. Other types of, what does it look like here if I were to pick a point, right? And here's my little vector. That's the direction I'm going, right? Notice that this makes a 90-degree angle to this radial line here, right? This is a radial line. And so what does F dot dl look like? Where this is my little dl. This is the path I'm taking, right? Well, it's at 90 degrees to this radial line. So this is like the magnitude of F times the magnitude of this little dl times the cosine of the angle between them. But the cosine, the angle is 90 degrees, right? And what is the cosine of 90 degrees? 0. 0, right? So this goes to 0. So there's no force acting along this path, you see? That's why it doesn't take any work, right? Because if there's no force, then any displacement that you make with no force is no work, okay? An easier way to understand and think about these equipotential surfaces is a cartographer's map, okay? So imagine the following. So this is on a map of, say, a mountain or a large hill, okay? And these dotted lines that I've drawn here, right, so it's like an aerial view from above, right? And the lines that I've drawn here are lines of equal altitude, okay? That's feet above sea level or whatever, right? So you can kind of see the hill, right? Can you see the hill based on these lines that I've drawn?
Yes.
Yeah, right? So you're familiar with that. Now if I roll something off the hill from any of these points along here, right? If I roll something off the hill right here, which way does it go? I'm not pushing it, I just let it go. Which way is it going to roll?
Down.
Well, down, yes, but which way is that in the drawing? Is it like this? Is it like this? Is it like this? What is the direction for it? You just have to imagine it in your mind. You're looking at you've got your drone flying above this hill. Somebody's standing at this point right here. They let a ball go to roll down the hill. Which way is it going to go? Is it going to go that way?
No.
Is it going to go around this curve? No. You imagine a little line right there, right? It'll always be perpendicular to that line. That's the direction that it goes, okay? Yeah, so the lines of force are always perpendicular to the equipotential surfaces, okay? And that'll be useful. So let me see if we can draw a picture for a dipole. That's a tough one, but let's give it a try. Here's a positive charge, here's a negative charge. Well, we need to find perpendiculars to this. Here's a perpendicular to this, right? So we could have an equipotential sheet all along this point here where this shouldn't be, looks like it's tilted, but it shouldn't be, okay? What else would you get? You'd also get these kind of, something like that. Many of them though, you get larger and larger, like, they're not spheres, I guess you call them spheroids or something, right? These balls, and then we got this flat sheet, right? Those are all equipotential surfaces, okay? So you can see it can get quite complicated, but you have to draw them such that at every point where they hit one of these lines that they're perpendicular to it, right, to a field line, all right? I tried to do that, but maybe it's not the greatest job in the world, right? Again, these equipotential surfaces are places where you're free to move around, a charge is free to move around without doing any work, okay? Could be pretty useful, and I'll give you, here's an interesting tidbit to just think about. And we'll probably talk more about it later. But conductors, right, are equipotential surfaces, right? Charges can move around freely.
Yeah.
Okay? So that means if I bring a piece of metal and bring it into contact with something that's at that has a certain amount of potential energy, I guess you could say, then it will have the same amount of potential energy, right? The charges will move around in such a way that this will happen. And we'll talk more about that in our next lesson when we talk about electric potential, which is different than electric potential energy, okay? Right? It's a little bit like the field is to the force, the electric potential is to the electric potential energy. I know it gets confusing, but it turns out these constructions are actually very useful, okay? As you'll see, okay? Let's put it to use, though. So let's just look at the potential energy for multiple charges. Really, we're going to look at the work that we need to do in order to bring together, a bunch of charges, all right? So we'll start by bringing in the first charge, and as you remember, to bring in this charge Q1, it took 0 work, right? So let's tally up our work here. Work is equal to 0, right?
Yeah.
Now let's bring in another charge. Doesn't really matter where we put it, Q2, okay? So we need to add the work to do that, but we know what that is. The work is just K, Q1, Q2, divided by R12, the distance between them, right? So however close it is to this charge here, that's the work we need to do, right? To bring it in from infinity, so pull it way far away, like, way out the door, right? Down the street, bring it in to this separation R12. Understand?
Yeah.
And that's just, this is that work, which is the negative of the potential energy for a single point charge, okay? So we're doing it one charge at a time, all right? Let's bring in another charge. Bring in Q3, put it right here, right? And it'll be at a distance from charge Q1 of R13, R13. I always switch the order that I do these things. Right now I have it saying R13. It's like the smallest number to biggest number. Really, I think it should be, this one should have been called R21, 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 and this should have been called R31. Right? But there's also the separation here between this charge, right? So this will be R32. So when I add up the work for bringing in this third charge, right? Remember, this is the work for bringing in the first charge, Q1. This is the work I had to do to bring in the second charge, Q2, right? And this is the work I have to do to bring in the third charge. It's K, Q1, Q2, divided by R, it's Q3, sorry, Q1, Q3, R31. That's the work against this charge. But we also have this Q2 here that we have to deal with, plus K, Q2, Q3 over R32. Okay? Yeah. So, but let's say this would be a real pain to have to do it for a bunch of charges, right? But let's at least come up with some kind of formula that we can use, maybe to program a computer to tell it how to incorporate some list of charges that we want to put in. So it loads up a file that has 1,000 or 100,000 or a million charges in it, and the locations you would like them to be, and then it runs through some algorithm to figure out what the work is to do that. Okay? So let me just rearrange the order of this a little bit. So I'm going to write it as K, Q2, Q1 over R. I'm going to change my order yet again. R21 plus, what's the next term I want? K31. So K, Q3, Q1 over R. Am I going to go 3-1? Yes, R31. Plus, the last one that's missing is K, Q2, Q1 over R21. Okay? And if you find somebody smart to figure out how to put this into a summation formula, right? Because what you want to do is you want to do a sum. In this case, we have to do two sums, okay? I, which is going to start at 2, and we'll go up to n. That's where n is the number of charges we have, okay? But we'll need another sum here for j, which starts at 1 and goes up to I minus 1, of k, qi, qj, divided by rij. Okay? So if you look at this formula and think about it long enough, you'll be able to see how this formula could map it in. Let's try it, just to make sure we get the right thing, okay? So we've got 3, we're going to let n be equal to 3, okay? So what are the terms that we're going to get? I'm just going to write it like this. I'm going to say we're going to get the first term is going to be some work term where we have I is equal to 2, j will be equal to 1, of course, right? Now can we have j be equal to 2? No, because this counter, the second counter, only goes up to I minus 1. I was 2, so 2 minus 1 is 1, so it only got the one term. The next term, right, will be w, where I is equal to the next integer after 2 would be 3, so that'll be 3, which means this can go up to 3 minus 1 or up to 2. So we'll have a 3, 1 plus a w, 3, 2 term, right? And since I is equal to 3 and we went up to 3, we're done, right? That's our complete sum right there, okay? So these are the three terms we get, and you can kind of see that it's going to map onto this real nice, right? So W21, that's just going to be letting I be 2 and j be 1. All right, so I fixed this. I had mislabeled a few terms. I put this term in twice, basically. I needed to have this term in instead. So I fixed that here. And we see that using our formula, we do map nicely onto what we started with. So this is a formula that you can use, and you'll have to use it in your homework. And some of the questions I'd like you to ponder when doing your homework are things like, does it matter the order in which I put these charges in? If I started with, say, Q3 first, and then did Q2 and then Q1, or maybe I start with Q2 and put that in first, right? Think about whether that's going to matter at all, okay? And other things, like, well, if I were to, move Q3 around in some, in a circle, and then swing back around to here again, did I do any work? No, conservative force. Conservative force means if your ending point is your starting point, you did no work, okay? Now in real life we have things like friction, which are not conservative forces, and so that always means there's some work involved in stuff, right? Even if I roll a ball up a hill, there's some friction, right? Yeah. So there's that. And next time, so this is not the prettiest formula in the world, I agree. It looks kind of nasty, and I don't know that you're going to find it in any books anywhere, but it's correct, it does work. The nice thing about it is you don't have to worry about messing up the indices. It'll just run straight through in a computer, put it in, it's going to work fine. Next time, when we talk about potential, I'll show you another way and a slightly easier formula that you will find in books, but at the expense of having to do some thinking whenever you put things together. You have to go, okay, well, I'm never going to have I and j be the same number. As long as I don't do that, the formula is going to work nicely. Okay? But that's for next time. I think that is pretty much it, all I had on this. Any questions? No? Everybody understand? It's so simple, isn't it? Sure. I heard someone on the internet complaining. He was an MIT student, a former MIT student, maybe he's a current MIT student, complaining that when he's there, he always gets people that explain things to him, and he doesn't have a clue what they're talking about. And it makes him feel dumb because they think it's so trivial. They're like, oh, it's trivial. This is nothing. This is simple. And yeah, I've probably been on both sides of that equation in the past. But so you have to let me know if something just totally doesn't make sense. Okay? All right. That's it for now. Ah, and the storm is over. Power's back on. That's great.